Okay, welcome everybody again to Optimization Oslo. We're very happy to have our first lecture of this, I guess, not springtime here in Norway, but in other parts of the world. So today we have Professor Paul Mans from TU Dortmund. He's going to talk about regularization and integer optimal control, lessons learned, and challenges ahead. So, Paul.
Okay, yeah, thank you very much for the kind introduction, Thomas, and the nice invitation to come to Oslo. And yeah, so what I'm presenting today will be, has its root actually in my PhD thesis. And ever since completing it, I was thinking about how to regularize these problems to make them behave better, because I was not satisfied. So I start with showing you with what I was not really satisfied. So we have an integer control problem here. And the problem formulation leans on an article from 2015 from Coop by Haslinger and Mäkinen. And what do we see here? So on the left-hand side, we have the real part, or the modulus of the real part of what is called an instant wave y0. And it says, so the values are low where it's blue and high where it's red. And what we want to minimize, or what we want to do, is we want to design a scattering device. So we want to design a device in this green colored area that maps from points in this area to three artificially chosen, in this case, material constants 0, 1, and 2. So that the resulting scattered wave y plus y0, that gives us a damping of the observed modulus of the wave in this gray colored area. And the scattering is governed by this Helmholtz equation here on top. And if you apply the algorithms that come to, or most of the idea coming from my PhD thesis, then you end up with the following design here. So the value 2 corresponds to black color, 1 to gray color, and 0 to white color. And while the damping seems to work quite nicely, the design is far from being perfect, because you have these high oscillations here, right? So it will be very difficult to manufacture this design actually. So this is the problem where regularization shall come in, right? And we'll see how that works in a minute. So this problem is an instance of a more general problem class that I call P for now. So the objective is to minimize a function J that depends continuously on y, and y is the solution of, for example, some PDE, ODE integral operator, which we abbreviate by the solution operator of some dynamics S. And the input to S, this is a function W that is only allowed to take finitely many values. And for this talk, we only allow for integers, but that's generalized. So these are the three material constants in our example. So, and there are different ways you could approach this problem. So the first thing one might think of, and it's not a bad thing to think of that, is you could just discretize this whole optimization problem. And then you end up with a very large mixed integer nonlinear problem. And then you try to solve it with the established algorithms or with the techniques for mixed integer nonlinear programming. And unfortunately, you kind of add two problems together. So you have this general thing that mixed integer program gives you this curse of dimensionality, and you have additionally many variables. So you increase the dimensionality even more because you have to discretize the PDE and the control, etc. So this does not scale well, this approach. And so another idea one could follow is to drop the discreteness constraint here for a moment and then see what happens to this problem. This is what I would call relaxation-based approaches. And the very nice situation actually occurs if you can prove that if you solve the continuous relaxation of P, meaning you allow for values in the convex hull instead of only the discrete values. And then you can sometimes prove under certain conditions on S and J and its derivative that the solution will already be integer valued, will already take the values you want to have. So this is called the bang-bang principle then. And if you have a bang-bang principle, this is of course nice, because then you solve the relaxation and you're done. Unfortunately, that is not often available, or often it may not be available. And then one can, for example, resort to what I would call regularization-based approaches. For example, you could add L1 regularization, or what Christian Klaas and Kunisch introduced in this 2014 article, multi-bank regularization. And what you want to do is you solve a convex relaxation or a continuous relaxation where you allow for values in a convex hull here, but you add also a regularizer penalty term to your objective so that you promote these discrete realizations W1 to Wm. And a third approach, one that I spent much time with in my PhD time, is the so-called combinatorial integral approximation. There you compute a solution of a continuous relaxation of P, and then what you do is you compute a close discrete valued control that is close to the continuous fractional valued solution of the relaxation. And close means usually in a weaker topology than the usual LP topology, so something like weak star in L infinity. So this is so these are different ways, and I want to, since I spent much time on that, and this led to several ideas for regularization, I'll briefly explain what happens if you follow this relaxation-based approach with the combinatorial integral approximation. So we have this problem P, and then we get the continuous relaxation R by allowing now for values in the convex hull of this discrete realization. So this is what I call R now. So and then one of the key insights here is that under fairly mild conditions on the operator S, you can actually prove that the infimal value of the problem P is the infimal value of the problem R, and the problem R usually has a minimizer. The problem P does not necessarily have a minimizer, may not have one, but the problem R has a minimizer, and we can show that the infimal values coincide, and you can exploit that algorithmically then in this combinatorial integral approximation part. However, what you compute then are designs like the one that we have seen on the first slide. So there's this same design here, the same control variable, where you have these high oscillations that try to approximate that is something that's actually fractional valued. And this optimized function W, that is way too complicated, and at least in my opinion here, to be implemented. And this drives, of course, the need for changing the problem or changing the solution process. So Wikipedia says that regularization wants you to change the problem so that the answer to our problem is simpler in some sense. So this is exactly what we would like to have. We want to have a simpler design without giving much away in the original objective. So the combinatorial integral approximation consists basically of two steps. So you solve the continuous relaxation to global optimality in a convex case, otherwise, for example, to a stationary point. And then you approximate the solution of the continuous relaxation weakly star with discrete valued control. So in both steps, you can inject some kind of regularization. This is the first thing I've tried. So let's consider regularizing the first step. So what we can do is we can add a term capital G to the objectives of P and R. So we add plus G of W there. You would usually scale G, but I'll disregard it for now, right? You scale it by a constant. So, and then we have again the problem P and its continuous relaxation. So one important thing is that if you do not take special care, you lose this nice property that actually is behind the combinatorial integral approximation, that the minimum of R is the infimal value of P. So if we have a regularizer that is given as some integration over a scalar valued function that takes in this control W and integrates over the domain, and this function little g, the integrand of this regularizer, is strictly convex. So for example, as you have with the Tikhonov regularizer, L2 squared, then we immediately lose this optimality principle. Unless our solution of the continuous relaxation is not already optimal or discrete valued, then we now have suddenly a gap between P and R. So this is so tells us so not everything is allowed here if you want to follow the combinatorial integral approximation approach. However, there's some hope. If you think of L1 norm instead of the L2 norm squared, this guy is also convex, but it is not strictly convex, right? If you think of it, you have these two linear slopes actually, and it promotes W to be 0 or at the bounds if you have bounds right here on your convex file. So this is what the L1 norm would do, and this can be generalized. And here I followed the ideas of Klassen and Kunisch and reformulated what they introduced with multibank regularization. So we can define a function capital G, so a regularizer, again, pointwise as the integration over a scalar valued function, G of W, that has pointwise the form of a linear program where you have different values and you're actually optimizing over a convex combination of them. So this looks a bit strange, but what it actually is, it can be nicely characterized. So this function G is well defined. So you end up with something measurable, although you solve a linear program pointwise in your domain. And it's also Lipschitz continuous. The values it has are defined on the convex hull of W1 to Wm, and outside it's infinity, and its epigraph is actually a polyhedron. So it's a polyhedral function. So right, and so polyhedron generalizes this L1, and what of course you hope, and this is also what the literature tells us, this polyhedron then promotes the values W1, Wm that corresponds to these GIs, right? So you can encode some kind of precedence between them, and you have.
Did you define GI?
No, that's what you can. So that's a degree of freedom in your problem formulation. What the GIs shall be.
Okay.
So right. So you, for example, if you want that W1 to Wm shall have a precedence, so that W1 is lowest priority and Wm is highest priority, then you would put a very large value of G1 and a low value on Gm, and so you get some precedence. But you can, it's even more complicated because you can do it in a vector valued fashion, but you can encode precedence of these values by means of these GIs. And they are called, then these pairs are called banks, and that's why it's called multi-bank regularizer, and it promotes actually values at these vertices Wi, Gi. And every polyhedral function actually with bounded domain can be written in this form. And the nice thing is that with this regularizer, we can make this combinatorial integral approximation work, because under the assumption that comes from our PDE that our reduced objective J composed of the solution operators weakly star sequentially continuous, for example, if J is continuous and S compact solution operator of a PDE, and G is such a relaxed multibank regularizer, then you can constructively produce sequences so that you are minimizing sequences for P and converge weakly star again to a minimizer of R, so that you retain this property on which this combinatorial integral approximation builds. So this is one possibility that you can do. So there's another possibility, and this is the second step of the combinatorial integral approximation. There you can also insert regularization. So behind this is the following observation. So we have a solution of our continuous relaxation, which I call W, and then we have a discrete value. So this is are not integer values, unfortunately, because it's from a different example, and I didn't realize it until this morning. But as I said, everything works also for discrete values that are not integers here. So we are approximating this gray function weakly star in L infinity with this blue function W star here on the left and with W dagger on the right. And W dagger has certainly much less switching than W star, but the approximation quality is very similar. They are basically equal. And the question is, how could we get W dagger instead of W star? And the solution we came up with in Braunschweig was minimize now switching costs in this approximation step, right? So you prescribe a certain approximation quality, and then for this approximation quality, you minimize the switching. So in the end, if you drive your grids to very small interval lengths, you of course get high oscillations again. But if you fix the discretization at some point, or if you stop, if you're fine with some approximation quality, then you can at least do as good as possible regarding the switching. So this is called switching cost-aware rounding, and it was joint work back in Braunschweig with Felix, Christoph, and Christian. And the switching cost-aware rounding in the second step of the combinatorial integral approximation can be also written down as an optimization problem. So we minimize the switching of a function v. We want v to be discrete valued, and w is the solution of our continuous relaxation, and we have some way to measure the distance between w and v. So you usually, can come up with metrics that metricize the weak star topology in L infinity that you can prescribe here, and on a fixed grid, you always have a null space. So what you solve actually in practice is a pseudo metric here, fixed grid. And the observation, we made this in 1D. So if we have only a time-dependent problem, for example, the discretization of this problem on the grid we are operating on can be actually reformulated as a shortest path search over a directed acyclic graph under appropriate assumptions on the switching costs. And moreover, we were able to give bounds on the number of vertices and arcs in this graph. So this, of course, allows them to apply efficient shortest path algorithms to actually solve this problem in practice. Okay, however, these are the two regularization methods we came about in this combinatorial integral approximation, and there are limits to that. So the first thing is that this switching cost-aware rounding does not carry over nicely to multidimensional domains. So we ran into trouble getting it flying there because the resulting integer programs get really costly, and this nice DAG structure relies on the fact that we have this one-dimensional domain where we have this clear ordering along the time axis, which we do not have anymore in multidimensional domains. So that does not work nicely in multidimensional domains, and the relaxed multibank regularization cannot always prevent chattering. So what you here see is actually a result where we applied relaxed multibank regularization, and I think also at least a heuristic way of approaching switching cost-aware rounding in 1D, and you still have these high oscillations, this high chattering that we wanted to avoid in the first place. So that's a bit unfortunate. And the reason why this is the case is deeply rooted in analysis. I would say it's what is called Lyapunov's convexity theorem. So the Lyapunov convexity theorem says that if we consider our feasible set of controls, right, we have functions that are bounded and measurable and take only finitely many values in this set capital W. If we consider which functions we can approximate with that in the weak star topology of L infinity in a weak sense, this is what you always get if you think of the direct method of calculus of variations when establishing existence of solutions, then we unfortunately get more than our feasible set itself, right? So it's not weakly star closed, and what we actually get are the functions that take values in the convex hull of W, right? This is also what we exploited for this approximation rounding algorithms in the first place, but it also has this drawback that it inevitably leads to these high oscillations if we have these fractional valued solutions of our continuous relaxations of stationary points. So the insight we take from the analysis of control problems is, if you want to do better, if you want to avoid it, then our weak star limits, right, should be W valued, or in other words, our feasible set in which we are optimizing in function space, that should be closed actually in the function space we're operating in. And what we then need is we want to improve our mode of convergence to pointwise convergence, which means that if we have our parameter space W for our functions W, we want to have some compactness here in the parameter space. Okay, so how could we achieve that? And there are two basically methods that I'd like to propose. So the first thing is we could consider functions in the, for our problem in the space of functions of bounded variations that have this that attain discrete values. So space of functions of bounded variations is a much smaller space, and we characterize what it means and which functions are included in it in a minute. And the important thing is weak star convergence in BV. So this is what you get for bounded sequences, for subsequences of bounded sequences, can be characterized by convergence in L1 in norm and boundedness of the total variation semi-norm that is part of BV. So norm convergence in L1 then gives pointwise convergence of this functions W for a subsequence that we so there's, if we have convergence in L1, then there exists a subsequence that converges pointwise, and this pointwise convergence of course gives immediately that the limit W will lie in the same set again, so we have this closedness with respect to this big star topology of our set of feasible functions. So our set is now closed, and our problems have minimizers, etc. So have minimizers, and what we lose, on the other hand, is to have a nice relationship to the continuous relaxation. There's an alternative to BV. So another thing one can think of is to take a Sobolev space with fractional exponent and choose the exponent small enough. I'll tell you in a minute what this is about and what this means. And then you actually have the same thing. Then you again can characterize weak star, or because it's a Hilbert space, also weak convergence in this fractional Sobolev space as norm convergence in L2 and boundedness of the corresponding semi-norm. And this again gives that our space is weakly closed, that our set of feasible functions is weakly closed, and we can deduce existence of minimizers in our feasible set, etc. So I'll talk briefly about our recent results with the HS semi-norm, which was joint work with Thomas, and which we talked also about today. And the key observation is that if you choose S smaller than 1/2 for one-dimensional domains here, and then we obtain that we lose the continuous embedding of our fractional Sobolev space into the space of continuous functions. So this means actually that we can allow for jumps now, right? This is what we need for discrete value functions, that we need to allow jumps. So a Sobolev space that embeds in the continuous function is not a great idea, because then the only feasible points are the constant functions, because there are no jumps. So we choose the fractional exponent less than 0.5 to get around it, but we still have this compact embedding of this fractional Sobolev space into the square integral functions that gives us then that our set is weakly closed. And then we consider this regularized problem where we have this H as semi-norm squared here as the regularizer. Again, you would usually scale that properly, but we leave that out here. So, and then we were able to obtain several characterizations. So revision was just submitted today. So assuming S is less than 0.5, and then this is kind of a negative result because or at least it failed at first because we didn't expect it. So we thought, okay, this chattering will go away completely, but turns out that's not the case. So we're able to construct a binary valued function that switches countably many often in each of countably many pairwise disjoint intervals. So you have a sequence of intervals that get smaller from right to left, and in each of them you have an accumulation point of chattering. However, this crazy chattering that is spread out everywhere that we have seen before, we were not able to reproduce in this space. The second characterization is more of the good news part. So what we actually were able to come up with is an optimality condition. So under mild assumptions on our optimization problem, meaning Lipschitz continuity of J actually, or J composed of S, functions in HS that switch infinitely many times in a small and isolated area. Also, if they switch only finitely many times in a small and isolated area, they cannot be optimal for Q. So you always have a big benefit if you have only a spurious switching locally to avoid that switching. So this gives you an optimality condition for this problem Q. And the characterization number 3 was we wanted to analyze if it makes sense to derive an optimality condition by assuming you have a fixed switching structure and want to check if your function is optimal. Can we perturb the switches a little bit and drive the perturbation to 0 and differentiate by it actually? But it turns out that this does not work for this HS semi-norm, so because we can become unbounded in this fraction 1 over h, so 1 over the perturbation of the difference of this HS semi-norm squared minus the unperturbed function. Okay, so this is the results that we've got so far for the HS semi-norm. And next thing is that I move to this other possibility that I've told you. So considering total variation. So this has been studied much longer, and there's of course much more literature already out there because many people in imaging are using total variation, right, for image reconstruction, etc. And this was joint work with Sven during my time at Argonne, or where it started basically. So we minimize, same problem as before, just that we exchanged the regularizer. So put out HS squared, insert total variation semi-norm, and then we make the same observations as before. This term enforces boundedness in BV, and under fairly mild assumptions, this problem has a minimizer. So the assumptions are so that the composition of J with the solution operator S is lower semi-continuous. You do not even need weak lower semi-continuity. I'm telling you that because I was asked several times about that. And you do not need it because you have the boundedness in BV, which gives you already norm convergence in L1, and because the set has L infinity bounds in all LP spaces with P less than infinity. So you only need lower semi-continuity and boundedness below. And then this problem Q, unlike this unregularized problem, has a minimizer, and this is really a corollary of all the literature on BV. And L1 balls around feasible points, this is of course very nice. Now they always contain further feasible points. So if you think of integer programming in finite dimensions, if you draw a little circle around your integer feasible point, what happens is that if this circle is small enough, the ball is small enough, then there will be no other feasible point, right? But in infinite dimensions with discreteness constraints, this is not true. It behaves more like if you were optimizing in Rn instead of the integers. So we always have feasible points. However, what we've lost is the vector space structure, right? It's not a vector space of feasible set anymore. But this gives rise to a meaningful definition of local optimality. So we say that a function is locally optimal if there's a positive radius, so that our objective is optimal in an L1 ball around our function. And if we know what locally optimal now means, then of course the question is, can we construct descent algorithm? What do they converge to locally optimal points or stationary points, what you would expect from nonlinear programming? And then is of course the next question, what does stationarity mean. Okay, so how the algorithmic work started was basically this trust region subproblem. So it's consists of several parts. So the idea is we assume we have a feasible function W for our optimization problem. We want to compute our next iterative in an algorithm. So we are optimizing W next. And here in the first part, we have a linearization of the objective we want to ultimately minimize, J composed with S. And here W next minus W is of course the step we're taking. And then we have the total variation difference between previous and between the new and the previous function. And then we want that our step is bounded by delta in L1, and the next iterate shall be feasible as well. So if you think that if you for a moment disregard the discreteness constraint and the total variation difference, then what you get up is some way of gradient of a gradient step. So and in our case it was difficult to insert subgradient of the total variation, so we just keep it exactly the TV difference here, and then we add this discreteness constraint, because of course in discrete setting there's no real gradient of this object, but we can still write down this trust region subproblem, and we know that for all delta greater 0 there are infinitely many feasible points. So then this subproblem has nice properties. It has a minimizer. Then what you may not see immediately, but turns out really useful if you run it in practice, is that imposing this trust region actually in the L1 norm and not putting the TV difference to the trust region, that allows for really non-trivial geometric changes of the level sets of W or from W to W next. So this gives us means for topology optimization to actually devise new topologies. The total variation semi-norm term that enforces the feasibility of our weak star accumulation points of the of limit points of sequences produced by the algorithm. And if we discretize our domain omega into intervals, if it's subset of R, or into polytopes if it's a subset of RD, then we actually obtain an integer linear program. So this is of course not ideal, because solving integer linear programs can still be hard, but at least there's no nonlinearity anymore. Okay, so and then we solve that repeatedly in what I call a reset trust region method. So our input is reset trust region radius and some initial feasible control function W naught. And then what we actually do in every out iteration, we solve trust region subproblems with decreasing trust region radii until the produced iterate is acceptable for our algorithm, with the usual acceptance criterion that the actual reduction achieved is at least a fraction of the predicted reduction, with the fraction being defined beforehand. And if we have accepted a step, then we reset the trust region radius to delta naught. So this is a bit an unfortunate change compared to usual trust region radii, but yeah, at the moment our convergence analysis uses this property. So we stole the idea from works on mathematical programs with complementarity constraints. So why does this algorithm work and what does it converge to? So we start with characterizing total variation semi-norm. So total variation semi-norm in 1D is the sum of the jump heights of our control function W. So a feasible control function can only have finitely many switches then actually, because right, we have only discretely or finitely many elements of our discrete set capital W, and so the minimum height between two of them is bounded below, so you can only have finitely many times if you want to have a finite semi-norm value. So and then what we can do is we can start by perturbing a switch of the function W from one realization to the next, and then we can analyze what our reduced objective does for this perturbation. Specifically, we can obtain conditions by means of what is called Dini derivatives on the positivity or negativity of these Dini derivatives that allow us to say, okay, if this is positive, then we can shift Ti a little to the left or to the right, and will definitely improve our objective of the transregion subproblem and also of the superordinate problem Q. And for this little perturbation, of course, you do not change the totalization semi-norm because the sum of the jumper instead stays the same. And and then taking things upside down, the absence of these conditions gives you an optimality condition, right? If such conditions are absent, then you do not, this is a requirement for optimality, because if you have something in like this, then you can always improve your objective by shifting a little to the left or right. So this optimality condition has a nicer interpretation in the space of continuous. If your reduced objective or its gradient of the reduced objective, that is a function, right? If you evaluate W, it's a function, for example, in L2. If it's already a continuous function, then the stationarity becomes that this continuous function evaluated the switching point is actually 0. So you get something that really closely resembles the Fermat principle that the derivative should be 0. For the stationarity condition to be true, and of course then also to prove that if this stationary condition is not satisfied, you will always find a new iterate in the algorithm. You need a regularity assumption on the Hessian of the reduced objective, which I will discuss in a moment. The results that I presented here can be improved. So there's a recent work by Jonas Marko and Gerd Maxmuth from Cottbus who have investigated this optimality condition and improved it, so more can be said here. Okay, so what are the asymptotics of the superordinate algorithm? So we produce a sequence of monotonically decreasing objective values, and then what we get is 3 possible outcomes. The sequence is finite and the final element is stationary and determinate, so that's good. Then the second possible outcome is that the sequence of accepted iterates is finite, the final element is stationary, but the inner loop does not terminate. So right, so we basically our transregion radius will at some point start tending towards 0, so we always decreasing it, but the limiting element of such a situation is so the last that we accepted will then be stationary, or the algorithm does not terminate, but the inner loop always terminates after finding many steps. Then the produced sequence actually has a weak star accumulation point in the space of functions of bounded variations, and also in our feasible set. This weak star accumulation point is not only feasible but also stationary, and the mode of convergence is actually a little better than weak star convergence. So weak star convergence is boundedness of total variation. Non-convergence is would be a convergence of the TV semi-norm, also of the difference. This is not the case here, but the total variation semi-norm values converge to the limiting total variation semi-norm value. So you don't have a jump at the end to the bottom like you have what you could have if you would only have weak star convergence. So let's discuss that a little bit. So what is the regularity condition on the Hessian? The regularity condition is actually that the Hessian needs to, the Hessian is a bilinear form, and if you put in C and eta from L1 into that, we require that this Hessian form evaluate xc and eta is less than a constant times the product of the L1 norms of these 2 inputs. And the reason is that we have here in the discrete setting with finitely many values an equivalence actually between the L2 norm squared and the L1 norm, right? So with positive constants. And at the same time, we achieve Cauchy decrease in linear part of the objective and in stationarity only with respect to the L1 norm. So bounding the remainder with only L2 norm squared is essentially the same as with the L1 norm. So that would not be feasible. So we need an improvement of the regularity that that the PDE, basically the solution operator S, has to give us to some way in order to get convergence to stationary points. So what the proof in one dimension heavily exploits at the moment is that the difference between the total duration semi-norm values is bounded below it, or in Z actually, if we work in Z, but that it's bounded below if it's non-zero. That is important. And the reset is at the moment required to avoid contraction at non-stationary points. Moreover, we need to sensibly scale the TV term, right? If you scale it too large, then you will always get 0 as an answer, or a constant, because then TV norm is 0 and dominates everything. And if you make it too small, you get insane chattering. So I've not a systematic way at the moment of choosing the scaling, but it's important. And what I would like also to tell you is what you see when you run the algorithm, and what also comes out of this strict mode of convergence, what you see is that at some, you have this sequence of heights of step functions, actually your control functions, and that settles after finitely many iterations, and only the exact positions vary, and this resembles basically, I think, so the set of the active set in NLP solvers. And what you could do then is you could detect this, and if you have sufficient regularity, you formulate an NLP on switching point optimization and run that with a second order method to make things faster. Okay, so very briefly, the recent work on the trust region subproblems. In 1D, we can apply the same trick as before. We have a shortest path search on layered direct acyclic graph. And then we get again that the number of nodes is linear in the discretization intervals. And then we can run dynamic programming algorithms, or A star, to solve the discretization. And so here is a picture. Basically, we have a dynamic programming algorithm that is called TOP, very similar to also what Marco and Wachsmuth analyzed. And then we have A star here in red, and general purpose IP solver, and you see IP solver is much slower. And then for the other two algorithms, it depends actually on the problem size. So top is very fast in small problems, but this heuristic by accelerated algorithm A star with a heuristic that can bypass parts of the graph has some advantage on small problem instances where the average here runtime is lower. Okay. Moreover, we can use also the combinatorial integral approximation to come up with an additional guess for this algorithm and speed up things and get improved objectives. So very briefly, I want to show you very recent work with Annika, also from Dortmund. So in the multidimensional case, total radiation is not the sum of the jump heights, but basically the sum of the interface lengths or areas between different level sets. Weighted by the jump heights over the respective interfaces. So here we have level set with a jump. And what we can actually do is we can define an ODE that corresponds to boundary perturbation here. And then for this boundary perturbation, we get a new decomposition of the domain into these level sets. And now we have a means to differentiate actually with respect to this perturbation parameter, which is called T here and H here. So we can differentiate actually with respect to that. And this gives you then a Fermat principle and an optimality condition. And on violation, the Cauchy decrease in L1 again, like before, it's only in L1, which then can be applied to deduce conversion of the algorithm under slightly more regularity. In particular, we need to assume here that the gradient of reduced objectives is actually a continuous function, so something that should also come of the regularity of your PDE operator. And then we get basically the same asymptotics as before. So what does it do to our example? So this was the result of the combinatorial integral approximation with all the regularization techniques that I've talked about before for the combinatorial integral approximation put in. Doesn't look super nice. And this is what the trust region method gives you. It takes a week to compute, and this takes 20 minutes. Okay, so there's a difference, right? So the analysis is nice, and also I think the design is nice on the right? So it's these sharp interfaces. You have this algorithm was initialized with 0, so you can get to a complicated topology. This is where it's really beneficial to have the trust region imposed only in L1. But yeah, so the discretization is unfortunately still an issue. So really briefly to wrap up, we want to regularize these problems. We have found a way that the regularized multiplane regularization and switching cost rounding work well, but fail on our example problems. So this drives the ideas to find new ways for regularization. HS regularization is promising. I think Thomas and my work is the first one. Actually, already we haven't found anything else on the market. So, and variation regularization, there's of course much more work that has been done in the literature for imaging, where we build on. There has been some work now, and this allows nice analysis. But yeah, numerical analysis actually, there are big gaps, right, between the implementation of this algorithm and the function space algorithm at the moment. And efficient solution of subproblems is extremely challenging on multidimensional domains and work in progress. And with this, I'm almost in time. Thank you for your attention, and I'm happy to take questions.
So any questions? So we don't have too much time because we have a special meeting today. Yeah. But I was curious about the way you designed the trust region algorithm, because usually, you have your trust region subproblem, you have some kind of solver like that calculates maybe an approximate solution, and then you take that and then you check the actual versus predicted decrease and so on, and then based on that value, you would sort of increase or decrease trust region radius. But here it's somehow decoupled from that, right? Because you have this inner loop where you're decreasing the radii until you're happy, and then you go out and you check, and then you start again. So I mean, what's the logic behind that? I mean,
okay, so where the idea comes from was basically MPEG algorithm Sven worked on, because we could have the trust region contracting, but not really see around our interface shift or perturbation. And basically what Sven told me is, okay, if you think of MPEGs, then you could reset the trust region so that if you're close enough to a kink, the kink will always lie in your trust region, right? So you cannot contract next to the kink kind of and never see it, because you're contracting it more and more while moving towards it. And so this actually helped. By doing this becomes a bit more like line search, right? A mutual reset, and this actually helped to get to this convergence proof and avoid contraction at non-stationary points.
And so you don't have an issue though that the radii will just go to zero, right? Because you said under certain regularity assumptions you can avoid that.
Yeah.
That's kind of the crucial point.
Yeah, right. That's the crucial point. Yeah, under this regularity, we also need this regularity assumption, not only the reset. Yeah. But yeah. So yeah, what the regularity assumption basically says is that the gradient of reduced objective, that has to be a continuous function, and the optimality condition says that that you relate the level set of the curvature, or some scaling of the level set of the curvature of your interface in this specific region to this function. So and of course there's no real way to interpret this if you're not continuous, right? We have this pointwise evaluation. So it's I guess there's some more deep insights that people from analysis would tell me about this, but that's kind of my naive understanding.
Good. Okay, so let's thank Paul again. In a few weeks, we'll be back.